One of the reasons I am on YouTube is to draw attention to ideas you might otherwise not have heard about. This is how Sabine Hossenfelder opens one of her latest videos, presenting her foundations of what correct, new, and interesting means when it comes to scientific ideas. By doing so, she claims some kind of almighty authority and presents herself as a gatekeeper. I am here to help you. And she continues, in the foundations of physics, it's rare to find genuinely new ideas that aren't obviously wrong. Let's have a look. And thereby positions herself as a judge of what counts for a genuinely new idea and what is not obviously wrong. In general, I don't think this is a bad idea. I think it's a good approach. And I'm not a physicist, but I like to think about the big questions, the nature of reality, the foundations of consciousness, what is life? I comment from a technical angle, but I'm also very much open to different views. Sabine has certainly built an impressive channel, and she speaks critically and makes people reflect and think critically about foundational questions, which I think is a really good thing. Lately, she has gotten a lot of critics, though, for not taking the topics into depth. So when I saw that my co-author, Florian Neukert, has now received a 10 out of 10 on Sabine's bullshit meter, it made me think how important it is to get in depth on the topic. So I want Florian to directly respond to that video and demystify some of the false claims and look at some of the misconceptions that Sabine had, and also talk about what the quantum memory matrix actually is. Sabine drops two main criticisms. One, the energy conservation violation. Where does the energy come from? Seems to violate the energy conservation, she says. And the second, the Lorentz invariance breakage. You can't chop space into Planck-length chunks without breaking Einstein's theories, she says. And I don't think that this is what Florian intends and is not the purpose of the quantum memory matrix. Instead, it enhances Einstein's theories. But Sabine moves straight to the verdict, 10 out of 10 on the bullshit meter. But then she also includes that it might actually be something. It might have a useful core. So when you get a 10 out of 10 on the bullshit meter and still gets the verdict that the idea might in principle be good, I think that's a great conversation starter. So I decided to take Florian on to have a chat on the quantum memory matrix and let him explain what it actually is and where Sabine gets this wrong.
Hey, great to be here and great to have this conversation. Yeah, I mean, I remember when you reached out last week and told me about the video. Have you seen it? I hadn't seen it back then, and I watched it. And first of all, I'm very grateful that people get into this topic and really try to deal with it. Understanding it in full detail may be a little challenging, so it will take a while because there is a big corpus of work out there. There is right now 13 papers around the quantum memory matrix. And in each of these papers, we outline what we're going to tackle next. So there are still open questions, but back to the 10 out of 10 scale, many more people reached out. And I thought maybe I have to reply to that. Yeah. So I think it's, as you said, it's a good conversation starter. I hold no grudge, but I think a couple of things need clarification and explanation. So and if we can do that today, great. And I hope many more questions will come, many more discussions, because I do not expect, like in science, you shouldn't, that because you have an idea, because you work something out, that everybody immediately accepts it. That's how science lives. So you've got to discuss things and refine. So I'm grateful that we can do that today. And as you said, we have a good conversation starter.
Yeah, that's great. I think you're on a point. There is a lot of rhetoric. Obviously, I get the point of, likes and followers and shares. But I think, putting it back to that, in a sense of progress and trying to come up with better explanations, I think that's a good way to look at it. But maybe if we start off with, like, in layman terms, what is the quantum memory matrix and what is it that you are trying to solve?
Absolutely. I think a good start would be to think of space a little differently, as we've been thinking before. So think of space not as being completely empty, but as a gigantic, really, really big quantum hard drive. It's made of, in the quantum memory matrix, it's made of tiny registers, not little bricks, more like addresses in a memory of a computer system that can store and return bits of quantum information whenever matter or light passes by. And when I say quantum information, that's the things that describe quantum systems like amplitudes, for examples, or probability amplitudes, entanglement, all these things. And now imagine back being in space, when something flies through space, a little of this quantum state is swapped into that local register of space-time. And later, that information can be swapped back. Nothing is copied, so I remember, but we can go into more detail later, but I remember one of the points of criticism was that there is the no cloning theorem in quantum physics, which of course I haven't forgotten. But the key is here that we're not cloning a quantum state. So a little of the quantum state of whatever goes through space is swapped into the register, and later that information can be swapped back. Nothing is copied, and no energy appears from nowhere. Also an important point, which we will discuss a little later. It's a reversible exchange, like imagine moving money between two bank accounts, for example. In terms of what we're trying to solve, there are many things. So we wrote the first paper on the black hole information paradox. There's one of the big questions in physics these days, in cosmology. Where does the information of things that fall into a black hole go after the black hole evaporates? So we know, because of Stephen Hawking, black holes evaporate over time, but quantum physics tells us that information cannot disappear. But that would be the process if we start thinking about black hole evaporation. So things fall in, disappear, the black hole disappears, nothing is left. Quantum physics doesn't allow that. And now we have to find a solution to that problem, and the quantum memory matrix in its current form is an attempt to solve that problem. But that's only the first thing that we did. So if black holes evaporate, question is, where does the information go? And in quantum memory matrix formalism, we say it is never being destroyed. So we don't have that contradiction. We rather say it is written into nearby registers and can, in principle, be read back. So unitarity, which is one of the core principles of quantum physics, is preserved. And importantly, too, the more violent regimes are, the more information is written. Black hole is a very violent regime. But basically, the more things happen, the more matter there is present, the more things are written. And that, in a later stage, led us to trying to explain dark matter. But we'll discuss that too. So I'll briefly go into the key points of the quantum memory matrix. What is it trying to solve? So dark matter is the next thing. If we think about imprints left in space-time, so long-lived imprints in these registers that we briefly outlined, then they weigh into gravity. Coarse-grained, they behave like extra invisible pressureless stuff. This is exactly how dark matter acts in all the equations. And this is also why we cannot directly see dark matter in the quantum memory matrix formalism. So it's an explanation for why is there gravity? Why don't we see the additional stuff there that causes that gravity? So it's caused by information which you cannot directly see. That will, of course, lead to the question, can you ever prove it? Yes. So you can. So there are a couple of experiments that we prepared and outlined. Most importantly, with the new Event Horizon telescope coming to life in 2028. So here, if we look at the photon rings of black holes, we should be able to see with the resolution that the new Event Horizon telescope will give us a change in the photon ring structure as compared to old theories. So we should be able to verify that quantum information, in that case also entanglement, causes space-time to curve. Now, there are a couple more things, and I'll only briefly mention these to be complete here where we currently stand. Dark energy, the late time push is also something that we're able to explain using the quantum memory matrix. When you think about dark matter, so we had that, causes gravity. Dark energy blows the universe up, pushes things apart. So even when nothing dramatic is happening, a uniform background imprint is left by ordinary processes in space-time, so by ordinary things. We don't need black holes always. Everything that happens in space-time. And that looks like a very smooth energy component with negative pressure, and that is a dark energy-like effect. And lastly, What we are, of course, also interested in, since we now have various explanations of or various directions that we can go with quantum memory matrix, we also want to bridge quantum physics and gravity, because it gives us a concrete way to talk about quantum information living in space itself while recovering the smooth space-time we test every day. That is the quantum memory matrix formalism and the program in a few sentences.
That's I especially like the last part of the bridging. And I think solving some of these open questions is obviously, as I said in the beginning, not like an endeavor that happens with the first approach, but it's a work in progress. And I think this is where we need to take some time to dig in deeper. But before we get into those points, I would also be curious about the naming convention. So why quantum? Why memory? And why matrix?
Absolutely. So I will admit that I'm not 100% happy with the name, but it has a reason. So it's not that we pulled it out of thin air. The first part, quantum, comes from being, because the stuff that is being written and read is quantum information. So the amplitudes, entanglement, etc., phases, and these swaps, so the things that we write and read, or that space-time writes and reads, are fully reversible and unitary. That's the quantum part. So memory then comes from how space-time behaves. Instead of being passive, a passive backdrop, it's now active. So space itself can store and later return part of a system state. And nothing is copied, again, importantly. It's a write-read cycle, not moving files between drives, so to say. So that's where the memory comes from. And matrix, so the last reason, it's because the last word, we have two reasons. So one reason is because it's an array of registers that we arranged across space-time. And the second is the imprint and retrieval rules are naturally written as matrices or linear maps, as we say in physics too, acting between the matter registers and the space registers. So it has a reason why it has that name, because of these three components. Quantum information is written, memory we store in spacetime or spacetime stores, and the matrix because of the formalism. So in short, you could say quantum is for what we store, memory for what the space does, and matrix because it's both a grid of registers and a set of linear maps that swap information between matter and space.
That's good. But you're not quite happy, so you might come up with an adaptation.
No, I remember, Sabine also said it sounds like, I think she said something like it sounds like a Netflix
survival,
movie.
Yeah, survival. And I saw some comments on that was like, why memory? And like, so I just wanted to get your like take on that. Yeah,
but it's not it's not the memory in the metaphysical or even human sense. It's just I think more of a computer, which also has memory, and people don't seem to complain about that.
Right. No, but it's a computational look at the foundations of reality being information processing and meaning being a part of information. It's basically, it's hard to grasp, right? And I think this is also where the bridging needs to be done. So if you could, like, there were two main points, as I mentioned, that Sabine got into two criticisms. The one, the extra energy problem, and the one around the Planck length chopping. Can you take on both and just explain why her assumptions here are wrong and why this is not a valid statement or are valid statements?
Absolutely, yeah. So I think there are a couple of reasons for why Sabina may have come to these conclusions. For one, of course, the naming convention. So when we talk about Planck length, then you got to go into the details of the publications and say how we use the term. Planck length is not a new term, but generally the questions that come up naturally arise probably because I'm not sure if anybody has read all the 13 publications out there on it. But let's start with the extra energy. So I remember she asked extra energy for dark matter. Where does it come from? It seems to violate the energy conservation. So, but just as a reminder, Energy is a conserved quantity. You cannot create energy. You cannot destroy it. All the energy in the universe that anybody is going to use anytime is already there. We can convert, but we cannot create and destroy. And that is very important in the quantum memory matrix too. We do not create new energy. Nothing new is created. During the interactions, ordinary matter does work in the imprint degrees of freedom in space. And energy is moved into the registers that we mentioned before and is moved back out of the registers. The total stress energy is locally conserved. So there's this term in Einstein's field equation, the stress energy the tensor. So the divergence of T mu nu is zero. This is why redistribution is happening and not a violation of the conservation of energy at all. On large scales, these long-lived imprints relax very slowly and behave like pressureless matter, which is why they look like dark matter. This is the thing I mentioned before with quantum information causing gravitational effects, entanglement being able to cause curvature of space-time, but is not directly visible. And we also choose the coupling so that the imprint energy is negligible in the early universe, keeping the standard early time constraints intact. So therefore, we don't violate the conservation of energy at all. Very important to keep that in mind. And second, I remember the other point of criticism, a prominent one in the video, was that we cannot chop space into Planck-sized chunks without breaking Einstein's equations. And also, I remember Sabine saying Planck length means nothing. So, very importantly, we do not claim rigid little cubes with fixed rulers. Our cells are addresses in quantum registers with finite information capacity per invariant causal region. So we think, again, in terms of memory, capacity, not caliper. Observers can disagree about measured length under boosts, but they agree about invariant spacetime volume and about the count of registers inside a given causal patch. So where things happen, where observers share the same information, they will agree. And the macroscopic register acts as a regulator. So what experiments probe is the emergent large-scale description after averaging over many, many cells. And that description is Lorentz symmetric to very high accuracy. Tiny violations would live at the cutoff scale far beyond current tests. And that again brings me to the testability very briefly, and we can of course talk more about this. There are a couple of things that we can already verify today, and there are a couple of things that we will be able to verify in the future. There is one thing that is essential for the quantum memory matrix. It's what we call the imprint retrieval cycle. So it's basically unitary operators, or how space-time writes into, or how information is written into space-time and retrieved again. That we tested on a quantum computer. So we took a real quantum system and designed an experiment that shows that the imprint retrieval cycle works. Is that already enough of proof that is everything is done now? No, it's not. But it's a strong indication and evidence that it can work that way, and that so actually the mechanism works. Now we need more evidence. So that's in physics generally why for a very long time people talk about theories versus laws. So I think quantum theory, it's still a theory. It's the most tested theory in physics, but still people say it's a theory. So it's very important. So I'm also not saying we have the quantum memory matrix law. We have a theory. We have to test it, but we can.
Yeah, I think that was the part that you missed out, that it's testable. And you mentioned when I reckon, and she had a comment on, isn't this just gravitational memory? And also she went into that. They say that the weight of information comes out roughly at right for dark matter. And then she said, I'm skeptical. Can you also comment on these 2 points?
Absolutely, yes. So gravitational memory is a different effect. Gravitational wave memory is a permanent classical displacement between test masses. The quantum memory matrix speaks about quantum memory. Remember the amplitudes, entanglement phases, the quantum properties of systems. So this is the information stored in local degrees of freedom of space. It's a different observable, different experiments. For detection, we look to cosmological signatures, and to controlled imprint and retrieval experiments on quantum hardware, not classical displacement interference. ometry. So that is a different way of thinking about things. We use quantum system to test it. We use the Event Horizon telescope to indirectly, so the data that is produced by that telescope, to indirectly verify it. So quantum information itself, we cannot see with the Event Horizon telescope. But if entanglement causes curvature as predicted, then we'll see an effect on the photon rings around the black holes, on the stuff falling in to black holes. That is something that can be verified. And we calculated that. So that brings me to the next point that you just mentioned, and also Sabina mentioned, which is they say the weight of information comes out roughly right for dark matter. Importantly, we don't just say that. We calculated it very rigorously. And the claim is not hand wave. So coarse grain, the imprint sector, contributes like an additional matter component and can be fitted against standard cosmology data. That is what I mean when we say we look at the data collected with the New Event Horizon telescope. And beyond fitting, the framework makes testable predictions then. So specific small shifts in weak lensing power at medium angular scales, that's the photon rings, and near constant late time equation of state very close to -1 with a small checkable redshift dependence. So cosmological redshift is when you look at things that recede, that move away, the faster they move away, the more redshift, the more the light that they emit is redshifted until it reaches us. And using that, you can calculate how far something is away and how fast something is moving away. So can use that too. So these are clear places to confirm or refute the idea. And then, of course, we have our tabletop experiments, so to say, which is quantum computers. What systems are better suitable to test quantum effects than quantum computers? Initially, they were even conceived as systems simulating quantum effects and all the other things that we do now, machine learning, optimization, etc., that came later. But the original thinking that went into quantum computers was build these systems to simulate quantum systems. So the original name quantum simulator comes from. And these we can do today already. We don't have to wait for the new data of the New Event Horizon telescope in 2028.
Yeah, maybe also you've mentioned a couple of times, but the whole essence that you misses out on the copy of the information. So you don't duplicate, you swap. Can you just like make a short statement on which you misses out here?
Yes, absolutely. So very good that this point was brought up because quantum physics doesn't allow us to copy information. You cannot have the state of one quantum system and copy that, let's say, in another quantum system. That's not possible. That is then when things like quantum teleportation come in. I know the name is very fancy. It's not really teleportation. It's basically just taking the information of a quantum state here, moving it over there, then you have it here, but this one is destroyed. So that is how things would work in quantum computing, for example, or quantum communication too. But generally, a valid point. So importantly, we do not copy. We do not violate the no cloning theorem. We swap. So information moves between matter and the imprint registers by a reversible map. So the global evolution stays unitary. I say this, as unitarity is another key pillar of quantum physics. Unitary means, say you have a quantum system, you apply a transformation to that quantum system, apply it again, and you get back the original state. And you cannot change the length of that quantum system. So that's very, very important in quantum computing, for example. We talk about vectors of unit length. They have the length of 1 because we're talking computational basis states, can either be 0 or 1. But all the vectors that you use to encode, depending on how many qubits you use, still are unitary. So you have the unit length 1. And that is fully compatible with the no cloning principle. So the quantum memory matrix, just to say it once more, does not violate the no cloning theorem.
Can I put you on a hot spot right now for a very like a one sentence answer to some of this criticism? Just like to comment on the first, I would say like there is no cloning theorem. Information can't be duplicated. What would you say?
Information cannot be duplicated. That is correct, yes.
Yeah, but what do you do? I mean, that topic is what is the misconception? When I say to you, like, Sabine's claim is information can't be duplicated, and you say we transfer, we don't copy.
Yeah. So maybe I used the term not thinking too much. So I said we swap. That is a term also commonly used in quantum computing. You have swap gates, so swap operations, but basically it means you trade places. So when you say the no cloning theorem is violated, then I say no, it is not, because we don't clone, we don't copy a state, we trade places, we swap. We're from here to there, that's it.
And to the claim that there are too many self-citations?
So what we do is we cite in a new paper on the quantum memory matrix old papers of the quantum memory matrix. It seems reasonable because, for example, when we work on dark matter, then a citation of the quantum memory matrix in terms of electromagnetism, the strong and the weak interaction, the black hole information paradox, that makes a lot of sense. I think self-citations are a problem if you only self-cite yourself. Luckily, if you look at any of the publications on the quantum memory matrix, I'm sure the number of citations, it's not I'm sure, I know the number of citations of others' work massively outweighs the self-citations. 40, 50, sometimes 80 citations. And as I mentioned before, we only have 13 papers on the quantum memory matrix. We cite those that are relevant to a paper that we're currently working on, but that is what it is. So we had the idea and came up with this framework. So who else would I cite on it?
Right, no, obviously. But I mean, as you see, it's not a 4-minute YouTube video to settle this and to get these things. But I think it's important to tackle these. And you thought a lot about potential criticisms that might occur. You heard claims such as you're just redefining dark matter. This is wordplay and not again. These are things that have come up. Are there other like criticism that Sabine missed out that you would like to highlight, that you have thought about or heard that you would like to set straight now that we are talking about the topic?
So yeah, and as I said before, every new framework, every new idea will spark discussion and conversation, which is good. And I'm sure there's more criticism. So what you just said, we are just redefining dark matter. I think that is one of the things that may come up. But I will reply, no, we don't, because quantum memory matrix adds a concrete sector with dynamics and the specific stress energy contribution that behaves like collisionless matter. And then again, I will come back to the tests. It fits the same cosmology test standards dark matter does and makes additional prediction for lensing and late time expansion. There are a couple more points of criticism probably that will come. So, for example, energy double counting with ordinary matter, but also here, matter and imprint sectors exchange energy. So again, I bring up that swap that we mentioned before. T mu nu divergence is 0. When one sector gains, another sector loses. So that's important. We move information, we don't copy. And many, many more, I'm sure, will come up and we'll be ready to discuss. So I hope this is what we're doing here, cause people to reflect and also reach out, hopefully, with questions. And any conversation, any discussion around the topic is much appreciated. And I'm grateful that people look into it.
One thing that I also saw in the comment section, and the two of us have already discussed, is the relationship to the Akashic Records. I think there was one comment saying, not the Akashic Records again, and we talked about this, and in a poetic sense, both these ideas imagines a universe that never forgets. But could you comment on how you, from a scientific standpoint, sees how the quantum memory matrix clearly distinguishes itself from the Akashic Records, and also if you see some similarities?
Yeah, absolutely. So first of all, I will have to admit that I did not know the Akashic Records until very recently. And it was a couple of times already, not only in the comments of Sabine's video, but also in other videos made on the quantum memory matrix, other posts, where I saw that people compare it to this Akashic Records. And what I learned is that it emerged from Hinduism, and it is sort of a cosmic memory. So everything that happens in the universe is conserved somehow. And I will say this is not a physics theory. It is spirituality. So I don't have much to contribute here. But I will say that some of the core ideas and thinking seem to be related. So for example, when people say cosmic events, everything that happens is remembered, that is basically also what we say with the quantum memory matrix. However, we do it from a physics point of view. So we don't talk about memories. We don't talk about life events, so to say. We talk about particles and energy moving through space-time and interacting with other particles.
Yeah, no, but I think, the whole idea that, the total preservation of events and a cosmos that remembers is probably appealing to a broad audience. And the, you could say like an esoteric philosophy, obviously does not resonate with most scientists or physicists, and you wouldn't find esoteric philosophy within physics and quantum information theory. So I think that's clear that these are coming at a worldview that is different from the foundation of how you look at the world. But I know the two of us, we've been pondering our sci-fi future, uniting science and philosophy in a couple of books already. And I obviously look forward to digging more into the quantum memory matrix for our next publications. But I think, having these discussions on the various schools of thought and the various foundations of how we perceive reality, I think it's important, not necessarily to move into a spiritual esoteric domain, but I think just to come up with ideas on how to make something testable. So I think there is contribution from these worldviews, and also obviously ancient methodologies and beliefs that were not explicable in a scientific way, but were belief systems that has ideas that can be pondered through science. Or how do you see that?
Yeah, absolutely. So I think it's always important to keep discussions going, conversations going, and not to refute ideas and concepts outright right away. So very important. So if there are connections to other fields, I hope people start exploring it. Maybe we start exploring it at some point in our sci-fi work. But again, it's important that we do not right away put things on the 10 out of 10 BS scale.
That's a good point. Yeah, and I was looking at like Nietzsche's eternal recurrence, and I was reading up a little bit, and I wrote a paper like where we had that "Will the universe remember you?" and I think obviously these are playing with thoughts and ideas, and the unification of Newtonian physics and general relativity and quantum physics and the various disciplines, and looking into like the spiritual belief system, and to neglect dimensions of exploration through first-hand experience from psychedelics or whatever. I think it's not even good science to neglect a lot of these things, even if they're not, to be tested in a scientific endeavor today. I think they're helpful to open doors. And as you said in the beginning, most likely the quantum memory matrix is not complete, but therefore you encourage people to come up with, ideas and thoughts and reflections and comments on it. But I think, as you said, giving it a 10 out of 10 on a BS scale or a BS meter, it's not the way to approach it. And I think, you explaining it in depth today just helps us, get more people on board to think thoroughly about it, and not just to leave it at the surface for a short YouTube videos. So, I mean, I think, Sabine joked about it, right? She said, if space really does never forget, I think this video or in this conversation and you coming on just talking about it, it's very important so that we have an accurate description of what the quantum memory matrix really is. Thank you for clarifying, and I've given you a lot lower lower number on my BS meter today. That's for sure.
Thank you so much. Yeah, no, I really appreciated the conversation, and I'm looking forward to more conversation on quantum memory matrix. And also, so what I have to say is I received tremendously positive feedback via emails. My email address is on all of the publications. I'm always the corresponding author. So we get really, really good feedback and many interesting thoughts and ideas on this topic. We'll continue.
That's good. Florian, thank you for clarifying and for leading the scientific endeavor in a positive manner, and also being very open to criticism and taking them head on.